Hello again, this is your instructor Jerry Pinter. Welcome to our video lecture on Chapter 3, Part 3. In this final part of our lecture on Chapter 3, we will be looking at filter theory, impedance, and phasors. So this lecture is basically an introduction to filter theory. So what is a filter? Well, there are two types of filters. There is a frequency shaping filter, which changes the shape of a system's frequency spectrum. And there is a frequency selective filter, which passes some frequencies while blocking others. We'll be mostly dealing with frequency selective filters in this lecture and in this course. There are many examples of filters in different disciplines of science and engineering. For example, in mechanics, filters are used to remove vibrations, for example, from an airplane or even from an automobile, such as your suspension system. In electronics, filters are very common. They're used to remove noise from signals. They're also used for things such as bass and treble control on audio equipment. In chemistry, sunscreen, you can think of that as a chemical optical filter whose purpose is to block ultraviolet rays. And in optics, filters are often used. For example, digital color imaging is done using RGB or red, green, blue filters. So how do filters work? Well, here's a block diagram that sort of explains the main idea of a filter. So here we have a system, which we'll call this system 1. And over here is our filter, which we'll call system 2. So as you know, a system is defined by its frequency response. So let's put for our regular system here, that we'll call this H1. So what we have going into our system, the input, is some frequency component. So we'll represent this as a complex exponential e to the j omega t at frequency omega. So we know that from earlier in this chapter, we learned about frequency response. So what this does is basically the output of this first system is just the system's frequency response, H1, multiplied by the input e to the j omega t. So this is the unfiltered system output. Now we're going to take this signal and we're going to pass it into our filter, which is system 2. So system 2, or the filter, has a frequency response which we'll call H2. But again, remember the way frequency response works. We just take whatever's going into the system, which is all this, and we multiply it by the frequency response, which is this. So you can see now what comes out of this total network here of two systems is the multiplication or product of H1 and H2. The two frequency responses are multiplied together, and then of course here is the original input signal e to the j omega t, which went in way over here. So we see that the unfiltered system's frequency response H1 of j omega is multiplied by the filter's frequency response H2 of j omega. Therefore, we can design the filter to reshape the system's overall frequency response. The main types of filters that we're going to encounter and deal with in this course are the following these are ideal frequency selective filters. And here we're talking about continuous time. We'll deal with discrete time filters at the end of this lecture. So there are four types of main filters. The first one is the ideal low-pass filter. So these are plots of the filter's frequency response, and this is the magnitude plot. So you can see the absolute value bars around h of j omega. So notice what this frequency response does. It's very simple. It has a value of 1 for low frequencies, all right, and then at some corner frequency, which we'll designate by omega sub c for corner, at the corner frequency, the filter basically shuts off and produces 0 output. So what this tells us is that any frequency between 0 and omega c, between 0 and the corner, will be passed by the filter, and it'll just do nothing to the input signal. It'll just multiply it by 1. But any frequency above the corner frequency will be completely blocked by this filter because the frequency response magnitude is 0. Okay, so this is called the pass band here. And one thing that's always leads to a little bit of confusion is, remember, frequency response, we also plot these negative frequencies here, which are not really physical frequencies, but this is sort of a mathematical artifact, if you will, of the Fourier series, which, remember, consists of complex conjugate paired terms with both negative and positive frequencies. So the actual physical frequencies that we're dealing with this filter or any filter basically start here at 0, and we can just think of looking at the right half of this frequency response. So the pass band is any frequency between 0 and this corner frequency. Now, the sort of the converse of the ideal low-pass filter is the ideal high-pass filter. So a high-pass filter passes high frequencies. So you can see its frequency response is 0 up to the corner frequency, and then the frequency response of the filter jumps up to 1, and anything above the corner frequency, it passes completely through the filter. So here the pass band is up here, and by the way, these low frequencies this is what's called the stop band for obvious reasons. A third type of filter that's very important and very practical is the ideal band pass filter. So if you look at the frequency response here, you can see what the band pass filter does is it basically only passes frequencies in this range right here between the low corner frequency and the high corner frequency. So that's what omega CL and omega CH stand for, corner low and corner high. So notice if frequency is in between these two corner frequencies, then the filter will pass it on perfectly. But if the frequency is outside of this pass band, for example, if it's over here or if it's over here, the filter will completely reject or block those frequencies. We'll see later in the course when we talk about communication systems that this is how a radio receiver works. A radio receiver, like the one, for example, in your car radio, has a bandpass filter like this that selects a specific frequency for the station that you're trying to listen to, and it rejects all of the other station frequencies that you're not listening to. Sort of the converse of the ideal bandpass filter is our last ideal filter here, and this is the ideal band stop filter, which is also called a notch filter, or sometimes it's called a trap. So you can see what this filter does is it basically passes everything except for usually it's a very narrow notch or a very narrow band of frequencies right here at this corner frequency, and it will remove that particular frequency from the rest of the frequencies that are trying to get through the filter. So this is a useful filter if you're trying to remove a particular noise signal that has a set frequency. For example, in audio equipment, there's often a 60 cycle hum, they call it, which comes from the fact that our alternating current in our wall outlets is 60 hertz. So sometimes in poorly made audio amplifiers, you can hear that 60 cycle hum. It's a real low hum, but it is very audible. So by putting a filter, a trap or a notch filter set to 60 hertz, we can selectively remove that noise from the audio and let everything else get through. So each of these filters has its own practical application and is important for various different applications. So in this course, we're going to be mostly interested in electronic filter design, not mechanical filters or optical filters or something like that. So for electronic filter design, there are two main broad classes of filters. There are passive filters and active filters. So a passive filter is designed using passive circuit elements. This includes resistors inductors, and capacitors. So these are typically called RLC filters, all right, for resistance, inductance, and capacitance. And you can put these letters in any order. You'll sometimes see this called LRC filter or RCL filter, etc. The other type of filter is called an active filter, and these are more sophisticated and complicated designs that use active circuit elements such as op-amps and integrated circuits. We are going to be dealing in this course with passive filters because they're much more simple to design and analyze and also build. And in fact, this is the type of filter that you're going to build at home for the filter project. So we'll have much more to say about this as we go through this course. The other thing I'd just like to mention here is that filter design theory is a very rich and diverse subject. In fact, if you're an electrical engineer, you can choose entire courses that are just dedicated to the subject of filter design. Just to give you a little hint of some of the diversity and complexity in filter design, just for a low-pass filter. So remember, our low-pass filter has a pass band here where the frequency response is 1, and then the filter is supposed to shut off for higher frequencies. So you can see in this plot here, these are 4 different types of filter that are designed and simulated in this plot. So there is the RC filter, which we're going to look at very shortly here, is this curve here, which you can see it is a low-pass filter, but obviously it's not a really good or selective filter because it has sort of this soft slope here. But you can see what this curve does is that at low frequencies, near 0 up here, the filter passes those frequencies perfectly. And then at high frequencies, way out here, notice that the RC filter rejects the frequencies because the frequency response is very small. It goes to 0. But because this filter, you can see, it has sort of a soft response here. It's not a very well-defined corner frequency per se. Now look at some of these other filters. For example, the Butterworth and the Chebyshev filter are both much closer to an ideal, what they sometimes call a brick wall filter, where the filter, is solid up here at 1, and then it just drops off like like there's a brick wall right here to block those frequencies higher than the corner frequency. And for example, the Butterworth filter, you can see it's a little softer here, but it also has a very smooth and there's no ripples or anything up in the passband. The Chebyshev filter has a sharper drop-off, which for some applications is a good thing, but it also suffers from some artifacts. There's a little bit of overshoot and there's some ringing up here. And so there's always trade-offs in filter design, and that's one of the things that makes it such an interesting subject. So let's start with an example. This is the simplest filter you can possibly make. This is a simple RC low-pass filter, and even though it's very simple and crude and is not a super high performing filter, there's a lot of applications where you really don't care or need a really high performing filter. You just want to basically pass low frequencies and block high frequencies, and in that case an RC filter will often do the job quite well. So what is an RC low-pass filter? Well, it's a very simple circuit. It has a resistor, R, and it has a capacitor, C, and they're connected like this. So here is our electronic system. This could, for example, be, let's say, a radio receiver. Okay, and let's say the radio receiver has kind of a weak, noisy signal, and it has a lot of high frequency like static and hissing, which can be very annoying to listen to. Well, if you pass that output here coming out of our radio into a simple RC filter like this, you can filter out a lot of that hiss and noise and static, scratchy sounds and so forth, and get a much nicer sound here. So how does this work? Well, so you can see the input to our filter here, we'll call this V sub S, and the output of the filter is taken here. This is V out or VO. Okay, and you can see the way the interconnections are made here between R and C. So let's go ahead and analyze this filter with the ultimate goal of finding the frequency response of this filter. So the first thing we need to do, we're going to do this, basically two different ways. We're going to do it the hard way first, and then I'm going to show you later in this lecture how to do this much, much more simply and efficiently, but it's going to require the use of phasors to do this. But for now, let's just do it the sort of brute force method. We're going to write a differential equation for this filter, which for this particular filter is pretty simple. We know for a resistor, we can use Ohm's law. So if we call the current coming into our filter here, notice I've labeled this I, and we're going to assume that no current flows out of the output here, okay, because this output is just a voltage output that we're going to sense, for example, with an amplifier or something like that. So our current goes through the resistor and down through the capacitor to ground here. So Ohm's law for the resistor, well, we have the voltage across the resistor is Vs minus V naught. So, you should know by now from your physics and electronics classes how to use Ohm's law. We have to, go in the direction of current. So this voltage minus this voltage, Vs minus V out, equals IR for Ohm's law. And then likewise, the current going through a capacitor, is equal to C times dV dt, where the voltage is, notice the voltage on the capacitor here is the output voltage. So it's dV out dt. All right, so what we can do is take this expression for current and substitute it into our equation up here for the resistor and rearrange, put all our output voltages on the left and our input voltage, which is Vs, on the right. And here we have our differential equation for this RC circuit. It's R times C times dV out dt plus V out equals Vs. All right, so what we can do now is treat this filter as an LTI system, because it is, and from that we can find the frequency response. So remember, the way to find frequency response is we let the input to our system be equal to e to the j omega t. All right, we learned this in part 1 of this chapter lecture. And the output, we know, is equal to the same input, e to the j omega t, multiplied by the frequency response, h of j omega. And we don't know what this is yet, okay? But we're gonna find this out next. All right. So at this point, here's a chance for you to do a little bit of the work here. Here's an activity for you to do. What you can do is take these expressions for Vs right here and V out right here and substitute them into this differential equation and solve for frequency response h of j omega. So this is how we're going to find the frequency response of this circuit. Now, one hint here is, notice you have to take the derivative of V out, but remember that h of j omega is not a function of time, so you can just treat it as a constant. So go ahead and pause the video and do this little activity here and see if you can come up for an expression for the frequency response h of j omega. Okay, so here are the solutions to the activity. We've got the differential equation here. We've got an expression for Vs. We've got an expression for V out. And all we're going to do is substitute these into our differential equation. So when we do this, notice we have to take the derivative of V out. So basically, we get a derivative of e to the j omega t. That brings a factor of j omega out to the front. So what happens is we have j omega RC times the frequency response h of j omega. Remember, h of j omega is not a function of time, so we don't have to differentiate it. We just leave it there like a constant. And then, of course, when we take the derivative of e to the j omega t, like I said, we get the j omega out in front, and we still have the e to the j omega t. The second term here, v out, we're just going to rewrite this, h times e to the j omega t, and then vs on the right is just e to the j omega t. Okay, so at this point, notice we can simplify significantly. Every term has e to the j omega t, which is nice. We can just cancel those out, resulting in this equation here. And remember what we're trying to do here is solve for h, the frequency response. So notice there's an h in both of these terms, so let's factor out an h. So we have h of j omega multiplied by, in parentheses, 1, which is this term here, plus j omega rc, which is this first term here, and that all is equal to 1. And finally, we can divide by all the stuff in the parentheses, and we get our RC low-pass filter frequency response. H of j omega is equal to 1 over 1 plus j omega RC. So hopefully you got this answer. If you didn't get this answer in the activity, I would recommend pausing the video again and going back and making sure that you can do this, because this is a pretty straightforward and simple calculation to determine h of j omega. So make sure you know how to do this before we go on to more complicated things coming up. All right, the last thing here is let's plot the magnitude of this function right here and compare it to an ideal low-pass filter. So, you know, to figure out the magnitude of this, well, this is something you did actually back in homework number 1. There was a question that had something very similar to this, and you had to find the magnitude and phase. So the magnitude of this, you know, you can get it by multiplying top and bottom by 1 plus j omega rc. Basically, what you're doing to find the magnitude is you're using the Pythagorean theorem here. So the magnitude here is 1 over the square root of 1 plus omega rc all squared. And if you plot this thing, you get this curve shown here in red. So here is our frequency response for our RC low-pass filter, and let's compare it to an ideal low-pass filter, which is shown in blue. So you can see that they have a couple of things in common. At very low frequencies, close to 0, notice they both approach 1. And at high frequencies, as omega gets very large, notice they both go to 0. So this RC filter does behave as a low-pass filter. Obviously, it's not perfect because it kind of has this soft slope here, but you can see that in the extreme cases of really low or really high frequencies, it does a perfect job in those cases. The other thing I should mention here is that the corner frequency here is defined as 1 over RC, because notice when omega is equal to 1 over RC, in other words, if you let omega here be 1 over RC, well, that cancels this RC, and we get 1 plus 1 squared, which is 2, and the square root of 2 is 1.414. The reciprocal of that is 0.707. So what this filter does is at the value, when omega is equal to 1 over RC, which, by the way, you know, that's 1 over the time constant, 1 over the RC time constant, then the frequency response produces 0.707, which is, you know, about right here in the plot. So this is a, you know, a nice way to characterize the RC filter. We can define the corner frequency as 1 over RC, and we see that it does behave as a low-pass filter. So we saw that our simple RC low-pass filter certainly is, you know, it works as a low-pass filter, but it's obviously not an ideal filter. So the question comes up, can we make it better? Can we improve the design? The simple RC filter that we just looked at is called a first-order filter because the differential equation, remember, just had a first derivative in it. So in other words, it was a first-order differential equation. Higher order filters, for example, second order, third order, fourth order, etc., more closely match the ideal filter properties. So look at this plot down here. So this is, again, showing the magnitude of frequency response. Here is this gray line here. This is our ideal low-pass filter. It's basically a brick wall with a corner or edge right here at the corner frequency. So you can see a first order filter is this red line out here, and obviously, you know, it doesn't it's not that close to our ideal filter in terms of this slope and everything like that. A second order filter looks like an improvement, right? We see a more steep slope, meaning this filter is going to turn off more quickly and reject these high frequencies more efficiently. And then as we go to higher order, third order and fourth order, you can see that we're starting to approach the ideal filter here. So obviously, the fourth order filter here is a much closer match, but obviously, well, maybe it's not that obvious, but this is going to be a much more complicated circuit, and it's going to be much more complicated to design and also to analyze. So again, there are trade-offs. The beauty of the first order filter is in its simplicity. You only need two parts, one resistor and one capacitor, and you can choose the values to move that, corner frequency wherever you want. So that's kind of nice. It's a very basic, simple filter. But if we need something that performs better, we're going to pay the price with more parts and more complexity. So we're going to look at second order filters later in the course for the filter project, and also in chapter 6 we'll be analyzing the second order filter in great detail. Okay, let's now sort of change gears here, and we're going to do a review of something that hopefully you already have a little bit of experience with, and that is the topics of phasors and impedance. So what I'm going to show you in the next several slides is a very basic and brief but fairly comprehensive complete review of phasors and impedance. And so these topics, phasors and impedance, were introduced, for example, if you took Physics 202 at Cal State San Marcos, you may have used Randall Knight's textbook. So if you did that, you may want to review the chapter on circuits, and in particular the chapter on AC circuits, because that's really where it introduced the concepts of phasors and impedance. If you took Physics 280, the Introduction to Electronics course, or are currently taking Physics 280, then this will give you a little more experience and exposure to these topics, because phasors and impedances are they're a little bit tricky because they deal with complex numbers, and it's somewhat abstract compared to just doing DC circuits and things like that. But I'm going to give you I'm going to assume that you really haven't seen any of this stuff before, but it would certainly help to review some of this on your own if you're struggling with some of these concepts. So the use of phasors and impedances are powerful tools for filter design and the analysis of many different types of electronic circuits. So let's start with the basics here. For a DC circuit, we use Ohm's law to relate current I, voltage V, and resistance R. So Ohm's law for DC circuits, of course, says V equals IR, and I should be a little careful here. The V is actually the voltage drop across the resistance R, and the I here is the current that goes through the resistance. Now, what is R? Well, R is the resistance, obviously, which is the voltage across it divided by the current going through it. But kind of conceptually, the idea here is that resistance is the opposition to DC current flow. So what our goal here is, it's to find the AC equivalent to Ohm's law. In other words, we want a version of Ohm's law that will work for a sinusoidally varying voltage and current, and at any frequency. Okay, so the way we can do this is we can assume that we're going to be dealing here with sinusoidal voltages and currents. In other words, they're oscillating. Okay, so our voltage, for example, is going to vary with time. It's going to have an amplitude of V naught, and we're going to use a cosine function to represent our voltage. And so this voltage is oscillating with a radian frequency of omega, and there also may be some phase constant here, phi, with a little v to remind us this is the voltage phase constant. Likewise, the current going through our circuit also will be varying with time. It will have some amplitude I naught. It will also be described by a cosine function. It'll have the same frequency, omega, as the voltage. And it'll also have its own phase constant here, phi sub I. And these two phase constants are probably going to be different. In most AC type circuits, these phase constants are different. In other words, the voltage and the current are probably going to be out of phase in general. They don't necessarily have to be in phase like they are through a resistor. Okay, so here's where we make a big leap now. We're going to use a complex exponential function called a phasor to represent voltage and current. And always with the case with phasors, and this is important, and you can use this in any engineering or physics class that uses phasors. And phasors are used in a variety of engineering and physics class, for example, optics and electromagnetism and electronics all use phasors. So whenever you're using a phasor, it is always implied that the actual physical part, in this case the voltage and the current, are the real parts of the phasors. Okay, because we live obviously in a real world, in the real universe. We can use complex numbers as tools, but remember that they are just representing real quantities that are measurable, such as voltage and current. So here are the phasor forms. We put this, and it depends on the textbook. I used here this little squiggly, I guess it's called a tilde, over the top of the letter there, and this just reminds us that it's a phasor, kind of like an arrow reminds us that it's a vector. So this phasor voltage here is defined as V naught. Remember, that's our amplitude. Now notice what we have here. We have, instead of a cosine function, we have e to the j omega t plus phi sub v. All right, so this is our complex exponential form of our voltage. And I can go ahead and distribute the j inside here and split apart the two exponential functions if I want there. Likewise, for current, there's a current phasor defined as I sub naught, or I naught, the amplitude. And then here is our complex exponential function, e to the j omega t plus phi sub I. And again, I can rewrite this by distributing the j inside there. So these are, obviously complex functions, right? They have a real part and an imaginary part. What we're really saying here is that we're implying that the actual physical voltage and current are the real parts of this. So, notice if we use Euler's formula, remember Euler's formula tells us that e to the j times anything is equal to cosine of that argument plus j times sine of that argument. So the real part of the phasor is just the cosine part. And notice this is exactly what our voltage signal was from the last slide. Our real voltage, V sub, as a function of time, is equal to V naught, the amplitude, times this cosine function of omega t plus the phase constant. So, this is what we would actually measure with a voltmeter or an oscilloscope. We can't, really measure a phasor, but we can use a phasor mathematically to calculate things. And that's what's so powerful about the phasor. Exponential functions are easier to multiply and divide than cosines and sines. And really, in a nutshell, this is why we use complex exponential functions in physics and engineering, because they're usually easier to work with compared to trying to multiply and add sines and cosines together. You have to use all these trigonometric identities and so forth that make things really complicated and tedious. So, the phasor is a great sort of model and tool to use, you can try to. Different textbooks will represent phasors in different ways. One way to think of this thing is sort of like a vector in the complex plane, and this vector is rotating around the complex plane at the radian frequency of omega, omega radians per second. And so this is the voltage vector or phasor. Notice its magnitude is its length, and that's V naught. And then this is the current phasor down here, with its own magnitude or length. And these things are kind of rotating together around and around. And the difference in angle between the two is the difference in phase angle between delta V and delta I. Okay, with all of that, we can now define impedance and Ohm's law for AC circuits. So Ohm's law for AC circuits, instead of V equals IR, we have V equals IZ, where V and I are the phasor voltage and current, and Z is called the impedance of the circuit or of the device that we're measuring here. So what is impedance? Well, you can think of impedance as the opposition to AC current flow, just like resistance was the opposition to DC current flow. Okay, so that's kind of a general sort of conceptual idea of what impedance is. More specifically, impedance is defined as the ratio of phasor voltage to phasor current. All right, just like R is equal to V over I for DC circuits. So if we, take these phasors up here and divide one by the other, we get, we can put this in two different forms. In polar form, we have V naught over I naught. That's out in front. That's the magnitude of the impedance phasor. And I'm sorry, the magnitude of the impedance, and then it has a phase angle given by the difference between the voltage phasor or voltage phase and current phase. So phi sub V minus phi sub I. The impedance Z can also be put into rectangular form. And again, remember back in chapter 1, you learned how to put complex numbers into either polar form or rectangular form. So here's a good example of, practical example of doing both. So when we put it in rectangular form, the real part of impedance is actually the resistance of the circuit, and the imaginary part of the impedance, all right, which is designated by X here, which is, next to the J, that is called the reactance of the circuit. Okay, so both of these forms, have their uses and their merits. Now, for our particular application in this course, we are going to need to use the impedance for the resistor, the capacitor, and the inductor. Okay, and this actually is a pretty basic and simple thing to do. In fact, it's pretty easy to prove or derive, but I'll spare you the details. Basically, my proof or derivation is shown here in the white box. This is for a resistor. It turns out for a resistor, this is kind of a trivial case. The impedance of a resistor, Z, is just equal to R. All right, so that can't be any easier there. So in other words, we can think of this resistor here on our circuit with resistance R. If we want to replace that by its equivalent impedance, well, we just use R for its impedance. Okay, so the resistor, not really a lot of excitement there. For capacitor, it's a whole different story. And again, you can go through my derivation here, but what a capacitance gives us for an impedance is 1 over j omega c. So we are going to basically replace, whenever we see a capacitor in a circuit, we're going to replace it with an impedance equal to 1 over j omega c. And finally, for an inductance, again, you can go through the steps here of proving this, but an inductance, L, is replaced by its impedance, which is j omega L. Okay? So putting all this together, and this is really what's important in this part of the lecture, are these three results here. We can kind of think of, in the time domain, we have a resistance, a capacitance, and an inductance, all right? We're going to work a lot of times in the frequency domain with their corresponding impedances. So a resistance, we just use R. For a capacitance, we use 1 over j omega c. And for an inductor or an inductance, we use j omega L. And remember that Ohm's law tells us that in a circuit here, with impedances like this, that V is equal to I times Z. Now, how do we use these impedances? Well, it turns out that the rules for impedances are very much the same or identical to the rules for resistors. So for example, if we have a circuit with three impedances like this in series, Z1, Z2, Z3, remember that the way to simplify this is just add the impedances together, just like we would for resistances. If we have two impedances in parallel, remember the rules for adding two parallel resistors. There are some different forms to show it, but one is you take the reciprocal of the sum of the reciprocal. So it would be 1 over, and on the bottom you have 1 over Z1 plus 1 over Z2. And you could simplify this also, get rid of some of these fractions, multiply top and bottom by Z1, Z2, and you'll get an equivalent form. On top you'll have Z1 times Z2, and on the bottom Z1 plus Z2. So that's another useful form that I should have put up here, but I didn't. All right, another one here, this one is extremely important. The voltage divider rule. If you haven't learned this or don't remember it, now is the time, because we're going to use this over and over. Whenever you have two impedances like this, or two resistances, and there is a voltage over here on the left, and this voltage here is, notice it's like halfway between, these two resistors and ground, or two impedances. So this works for resistances and for impedances. The voltage divider rule says that whenever we see this configuration here, the output voltage is equal to this bottom leg, which is Z2, divided by the sum of Z1 and Z2, multiplied by the input voltage. Okay, so in other words, these two impedances divide the input voltage here. They divide it depending on the values of Z1 and Z2 according to this relationship. So this one, you're going to hear me use this many times, not only in this chapter, but especially when we get to chapter 6 and we start talking about filters, we will be using the voltage divider rule. So make sure you're familiar with that. So our last thing here, one of our last steps here, and this is also very important because this is why we're doing all this impedance stuff, is that an LCR circuit is an LTI system. So we can use our previous system results to find the frequency response of any LCR circuit. So, kind of the idea here is if we have e to the j omega t going in, we have frequency response times e to the j omega t coming out. If we multiply this input here by v, or v naught, the amplitude, well then this just becomes the input phasor over here. And so the output here, notice we also had to multiply it by v. This v times e to the j omega t is our input phasor again. And remember, if this v in coming in, what we get coming out is v in multiplied by the frequency response. So from this last picture here, or diagram, we can solve for h of j omega. Just look at this equation right here. It's pretty simple. The frequency response is just equal to this voltage output phasor divided by the input voltage phasor. And so this gives us a way to determine the frequency response of any circuit by using impedances. We can use Ohm's law or the voltage divider rule, which is shown right here, to easily find the frequency response. So to show you what I mean and how simple this is, let's go on to our example. Okay, so you guys remember our simple RC low-pass filter, right? Here it is again. Remember, we had R here and C here. So remember, it took multiple steps to find the frequency response. And you guys, did some of the work yourself in the activity. We had to find the differential equation first, and then we had to substitute, the input and output voltage in and do, a bunch of steps, right? Well, watch how easy this is by using impedances. We take our circuit here, and all we do is replace R with R, all right, because that's the impedance. We replace C with 1 over j omega c, because that is the impedance of a capacitor. And notice this is a voltage divider. Here's our V in, or VS, whatever you want to call it. Here's our V out over here. So the voltage divider rule says that V out divided by Vs, which by the way is the frequency response, is given by this impedance, 1 over j omega c. Remember, it's the bottom leg on top, and on the underneath we put this whatever is here, R, plus the 1 over j omega c. And notice we've got fractions inside of fractions, so that's easy to eliminate. Just multiply every term here by j omega c. So we end up with 1 over, this term here becomes a 1. I'm going to put that in front. And then here we get j omega rc. And here it is. This is our frequency response. We basically did this with just, 2 quick steps. I didn't have to do any differential equations or substitutions or anything like that. We just replace circuit elements with their impedances, use either Ohm's law, or in this case I use the voltage divider rule to quickly find the frequency response, which is, remember, output over input. So this is one of the huge advantages of using in the impedance method, is that we can determine the frequency response of an electronic circuit very readily and efficiently without having to do a lot of extra steps. Okay, the last few slides of this lecture, I just want to briefly introduce discrete time digital filter design, because what we talked about up till now are continuous time filters, and in particular, we talked about some the RC filter and looked at that one. Now we're going to turn to digital filters, and which is a discrete time filter. So digital filters, again, this digital filter design is a rich subject. Entire advanced courses and textbooks exist just on digital filters. I remember as an undergrad at the University of Illinois back in the day, I took a full semester course just on digital filter design. That's the only thing we talked about for 15 weeks. So, obviously here we're going to barely scratch the surface. I'm going to show you, in about 10 or 15 minutes, just some basics about digital filter design. However, if you're interested in this topic and you think, you might be working for a company that's working on digital systems and digital filters and so forth, there is an extra credit assignment on digital filter design in the homework folder that you can do, and it'll step you through sort of as a tutorial on how to build and design and analyze digital filters. Okay, so let's look at an example. We're just going to look at 2 examples. The first one is I'm just going to show you this block diagram here. So this is something that we've seen before. So we've got our input sequence x of n coming in. Here's our output sequence y of n coming out, and notice that y of n is fed back through a delay. It's multiplied by a, and it's added to the input. Okay, so it's a very simple, this is a pretty basic discrete time system. So let's find the difference equation for this. So this is a good time to review how to do this. So remember, to find a difference equation, you basically have to label all the arrows. So I'm going to start at the output here. This is y of n. So obviously this signal coming down here is y of n. When it goes through a delay, it becomes y of n minus 1, and then it's multiplied by a, so it becomes a times y of n minus 1, and that is added to x of n to get x of n plus a y of n minus 1 coming out up here, and that, of course, we're back to where we started. That is all equal to y of n. So I can write my difference equation from this last step right up here. Y of n is equal to x of n plus a y n minus 1, and I'm going to just rearrange this. I'm going to put my y's on the left, like we remember this is how we usually do it, and put my x's, my inputs, on the right. So this is a first order difference equation. What this tells us is that this is a first order discrete time filter. All right, and so y of n minus a y of n minus 1 is equal to x of n. So to find the frequency response of this, we're going to use the same trick that we used in the earlier part of this lecture. We're going to set the input going into our filter to the complex exponential e to the j omega n, because we know then the output is equal to the frequency response, whatever the h is, multiplied by the input, e to the j omega n. So the next thing, and this is very similar to what you did in the activity earlier in this lecture, we're going to take this x and this y, and we're going to just simply substitute them right into this difference equation to get this result right here. H times e to the j omega n minus ah e to the j omega n minus 1 is equal to e to the j omega n. And I'm going to distribute this j omega inside the parentheses to split up those two exponential functions accordingly. And the reason I'm doing that is now, notice every term has an e to the j omega n. So I can just cross those off, and it simplifies down to h minus a times h times e to the minus j omega is equal to 1. We want to solve for the frequency response h. So let's factor out the h. Notice it's in both these terms here. And we have 1 for this term minus a times e to the minus j omega for that term. And that's all equal to 1. Finally, we can divide by everything in the parentheses here, and we get our discrete time filter frequency response. The frequency response, h of j omega, is equal to 1 over 1 minus a times e to the minus j omega. And remember, a is a number that we can set in this block diagram. So we can kind of design this filter by picking and choosing different values of a. So let's see what this thing looks like if we plot it. So again, here's our block diagram, and here's our frequency response that we just solved for. And if we plot the magnitude of this function, all right, so obviously to do that, you're going to have to do a little work. You're going to have to get rid of the j's here to figure out the magnitude. There's some different ways to do it. You probably want to use Euler's formula here, and then you're going to use the Pythagorean theorem, which is how you normally find the magnitude of a complex quantity. But when you do this, you end up with, this is the plot for, let's let a, you remember that's just this factor here, let's let a equal 0.6. This thing is going to have this shape right here. So notice this is a low-pass filter. For frequencies omega close to 0, the filter has a high output, all right, which means it's going to pass those frequencies. Now remember, for discrete time, high frequencies are pi, plus or minus pi. That's the highest possible frequency in discrete time. So the highest frequencies are right around pi here, and notice this is where the frequency response has its lowest value. So it's basically not completely rejecting these high frequencies, but it's close, right? It's killing them off compared to the low frequencies. Now, it's interesting that if we change the value of a to negative 0.6, look at the frequency response of this thing completely flips. Now it's at a minimum at low frequencies, and it's at a maximum or a peak here at pi, which are high frequencies. So now it's flipped, and this thing has become a high-pass filter. So again, this is a rather simple and crude filter. It just has a single delay element, a multiplier, and an adder. So as far as discrete time filters go, this is about as simple as you can get, but it obviously does the job. It passes, for example, this low-pass filter. It sends through low frequency signals, and it's at least partially blocks high frequency signals. We can get better performance by adding more delays, and that's going to make it a second order or third order or fourth order discrete time filter, etc. And we pay the price with more complexity and more hardware if we want to do that. Let me show you another example of a digital filter. This one is a little different. Here's the block diagram. So in this one, we can write the difference equation actually by inspection, because this is pretty simple. Notice the output here, y of n, the sequence, it's equal to two things. It's x of n multiplied by b naught. That's what this little coefficient here, we're multiplying that implies a multiplication. So we have b naught times xn, and then we have x of n minus 1, because it's sent through this delay, multiplied by b1 added to that. So our output, y of n, is equal to b naught x of n plus b1 x of n minus 1. And again, to figure out the frequency response, we're going to send our input, or set our input sequence to be e to the j omega n. Our output will then be h of j omega, the frequency response, times e to the j omega n. And we're going to substitute this x of n and this y of n into this equation right here. And so it's pretty simple and straightforward. I just made those substitutions here. Remember, when you have x of n minus 1, this n up here, becomes n minus 1 because it's delayed by 1. And then we can distribute the j omega, just kind of like we did on the last slide. And finally, we can cross off all these common terms. E to the j omega n appears in every term. And we can solve for h of j omega, which is equal to b naught plus b1 times e to the minus j omega. So let's plot this thing. And again, this is the magnitude of the filter's frequency response. So if you set b naught and b1 both to 0.5, we get a low-pass filter. All right, so look at this filter's frequency response. At low frequencies, near 0, this filter passes and sets the output exactly to 1. So, that's like an ideal low-pass filter. At high frequencies, near pi, notice the filter frequency response drops off to 0 as it should for a low-pass filter. Okay, so this is, again, a very simple and crude low-pass filter, but it does what it's supposed to do. By making one change, if we change B1 here to negative 0.5 instead of positive 0.5, then the frequency response flips, and now it becomes a high-pass filter. We have, basically low frequencies are blocked because the filter output is close to 0, and high frequencies over here at pi are passed through. You can see that the value of the output of the filter is 1, meaning it's just going to send that type of signal right through without doing anything to it. Okay, so that is our quick and dirty review of digital filter design. Again, if you're interested in pursuing this further, take a look at the extra credit assignment. Otherwise, we are done with Chapter 3 for now, and I will see all of you shortly in Chapter 4 next. Goodbye.